Hi everyone, I'm going to be going over question 62 from Chapter 7, Bingo Problems. This is kind of an interesting problem because it deals with two springs. Normally we deal with one, this one deals with two connected to the same block. So we have this little system here. We have a spring here and a spring here, and we're given the spring constants. The first one, it's 25 newtons per centimeter, and the second one is 20 newtons per centimeter. And then we know the mass of the block, which is 3 kilograms. Now, notice that the spring constants are in centimeters. We're also told that the block is moved 15 centimeters towards the right side. And so we're going to have to change the centimeters to meters, but we'll do that down the line once, well, I'll show you where we'll do it. But anyway, so part A is saying what is the max speed of this block? So it's being pushed over 15 centimeters and then let go. And then it says where in the motion does this occur? So of course we'll use our energy equations here, and so to do that, starting out, we know that our kinetic energy is 0 because it's being held, here. So we won't even put that, but we do know there's a lot of potential energy through the spring. So we'll have U1 equals, and then since we're finding the max speed, that'll mean that there's no potential energy at the end, but all kinetic. So U1 will equal K1. And we're not told anything about friction, so no work is being done. It's all just within this conserved system here. So we have potential energy 1 equals, that's actually K2. So here's our equation we're going to start with. Now let's break it up into the components. So the way to do that is we'll need to break up the potential energy into two because we have two different sources of potential energy. And so it'll be 1/2 K1 x1 squared plus 1/2. And then K2 is 1/2 mv squared. So we have that. And now we want to solve for this V2 here, or V2. Since that'll be our velocity, our max velocity, that is. So now what we need to do is solve for V2. So do the algebra. I'll speed it up a little bit just since we all know how to do algebra. We end up with V2 equals square root of K1 x1 squared plus K2 x2 squared over m. Alright, since the halves on both sides cancel, so we get that. Now, what we can do is, since the only unknown variable is the velocity, we can plug in the values we know and solve this. So that'll be V2 equals the square root. We know that K1 is 25. X1 we know is going to be 15, right? The distance that travels. And that's centimeters, remember. And that's squared plus K2, which is 20. And then X2, which is 15. and then the mass, which is 3 kilograms. And when we solve that out, we end up getting v squared is equal to 5.8 meters per second. So that's part A. So we found the max speed. But then the second part of part A wants to know when this speed occurs. So in a system, your max speed is always going to be at the equilibrium point, because anywhere that's not equilibrium, there's going to be some sort of force pushing back on it. And so, like for example, once this comes back past the equilibrium point, it's going to have the restoring forces of both of these springs acting on it. And so that's going to diminish the velocity. And so it's going to be that, and it's going to be at equilibrium. So that's it for part A. Part B now wants to know what the maximum compression of spring 1 is. And so let me erase this. So we know that when spring 1 is compressed the most is when spring 2 is going to be extended the most. And so with that, we know a whole bunch of things. So first of all, we need to use our equations, the energy equation. And honestly, we don't even really need to do that, because we know that this is going to be pushed in 15 centimeters. So that means, since this is in a closed system, these are both inversely proportionate to each other, right? As this one, maybe not inversely, but they are proportionate. So as this one grows, this one shortens, and vice versa. So as one is extended, the other is compressed. And so what we end up getting is that the maximum compression of this is going to be 15 centimeters. So that's the easy way of doing that. I mean, we can show it through the math though real fast. So what we'll do is, we know that the U1 is going to equal 1/2 K 1x1 squared plus 1/2 K2x2 squared. So this is the same as we did before. U2 is going to equal K at max So we have this. The max is just that where that x is maxed out. Since we know that compression of one will be the extension of the other. So now all we need to do is solve for this, where the x1 is maxed out. And so as we do that, we will set these equal to each other. It'll get really long. So it'll be 1/2 So now we have that, and we know that, like I said, that the compression of one is going to equal the amount that the other is extended. So we know that x1 equals x2. That's what we'll call it. And with that, we know that x max 1 equals x max 2. And so, since we know this, we can sub in x2 for x1 and x max 2 for x max 1 into this equation. So that means x2 is going to be x1 and x max 2 is going to be x max 1. So that helps us get rid of a couple of our variables. And then now all we do is solve it for the x max 1. So we can get rid of all the 1/2 because they're everywhere. So we can cancel those out. And then we can also group some things together, factor it. So we end up getting k1 plus k2 as times x1 squared equals, we can do the same thing over here, k1 plus, let's see, we're going to pull out max 1 times k1 plus k2. So this looks a lot better than this up here. This is much more manageable. So now all we need to do is solve for the x1. And really what we end up doing, since these are both the same, these cancel. So really we end up with x1 squared equals x max 1 squared. We can square root them both. We get x1 equals x max 1. We know x1 is equal 15 centimeters. And so we know that x max 1 equals 15 centimeters. So that's our answer. Now, I said earlier that we would need to convert everything to meters. I actually forgot that we didn't need to, since everything's given to us in centimeters. As long as we kept with those units, then we're fine. So yeah, that's that. So we know that the max compression of spring 1 is going to be 15 centimeters, which is exactly what we expected based on, you know, just the way these springs interact, and since there's no friction and everything like that. So anyway, thanks for watching. Hope you learned something. I'll see you in the next video.